Good evening, my friends. Let's get started with Lecture 7. Again, we'll start with a review from Lecture 6, and then we'll get into the materials for Lecture 7. Lecture 7 is a lot more drawing-based than Lecture 6 was. Lecture 6 was mostly calculations, so we've now moved into the part of the class where we're doing drawing and visualization as opposed to mathematics. For some of you, this is a great time. For some of us, me included, I am not a fan, but I'll see what I can do to make this interesting and fun for everybody involved. Okay, so let's get started on this. From last time, 64.85 grams of Na3PO4 were dissolved in 725.3 milliliters of water. What's the molar concentration of this solution? Oh dear Lord. All right, well, I need a couple of things to do this. One is a whiteboard. 2 is my calculator. All right, so let's take and talk about what information we were given. So 64.85 grams Na3PO4 dissolved in 725.3 milliliters of H2O. And I want to know, what is the molarity? So if I want to find molarity, I need to know moles per liter. I can convert this to get liters, and I can convert this to get moles. So let's talk about how we do that. 64.85 grams of Na3PO4. Awesome. I need to know what the molecular weight of that is to be able to do this calculation. So what is the molecular weight of that? Well, let's turn on our calculator so that we can get started with this. Na3. So Na3 of them, 3 times molecular weight of Na is listed as 22.99 on my periodic table, plus phosphorus, which is 30.97, plus 4 times the oxygen, which is 16.00. And that gives me a total of 163.94 for my molecular weight. Okay, so that's grams, that's grams. Now I'm left with moles of Na3PO4. I need to divide by 725.3 milliliters. And of course, I need to convert that from milliliters to liters. And I multiply by 1,000 to be able to do that. That will then give me an answer, 64.85 divided by the number that I just calculated, divided by 725.3, then I multiply by 1,000. And that gives me 0.54539. 1, 2, 3, 4 sig figs. 1, 2, 3, 4 sig figs. So 4 sig figs. So my answer should be 0.5454 moles per liter. Sweetness. All right, I can do this. Awesomeness. Well, let's go back and look at what's my next thing I want to do. The solution above is diluted by taking 15.32 milliliters of that solution and diluting it to a final volume of 25. What is the final molarity of the solution? Okay, so let's see if I got that. I'm going to take the solution that I calculated here, this one right here. I'm going to take 15.32 milliliters of that, and I'm going to dilute that to 25 milliliters. I want to know what the new molarity is. Well, this is a dilution problem, so I'm going to use M1V1 equals M2V2. Hopefully you can read that. This is M1, This is V1. This is V2. So I'm looking for M2. That's equal to M1 times V1 over V2. So 0.5454 molar. And I have 15.32 milliliters and 25 milliliters. Milliliters cancel, leaves me with an answer in molarity. If I do all of that happy math, yippee skippy, 0.5454. Oh, wait. So that number, which I haven't truncated with the rounding, I'm going to take that, I'm going to multiply that by 15.32. I'm going to divide that by 25. 0.3342, and again it's 4 sig figs. 0.3342, and that's molar. Oh, awesome! I did it. Go me. Let's see what we have next. A 64.38 milliliter sample of an unknown acid, HX, is reacted with NaOH. 27.32 milliliters of 0.00200 molar NaOH is required to neutralize the HX acid. What is the molarity of the acid? All right, let's start at the beginning. So I'm going to clear this and tell you what I see in looking at this. So I'm going to write down this volumes. I don't want that. I want that. 64.38 milliliters of HX. I know that HX is reacted with NaOH. 27.32 milliliters of NaOH, and it's 0.0200 molar. Okay, and that's required to neutralize the HX acid. All right, fine. What's the molarity of the acid? Well, first thing I need for this is to balance an equation, right? So I know that I have HX, and I'm reacting that with NaOH. And I know that I'm going to end up with, since it's neutralization, H2O plus some salt, which is NaX. Now, how do I know it's just NaX? Well, I had one H, and then this X, and I have one Na from the NaOH. That gives me with an H from the acid plus the OH from the base to make water. And that leaves me with Na and X. It's 1-to-1. It has to be, because I only have one acidic proton showing on HX. And I don't care what the rest of that X is. It really doesn't matter. The only acidic proton that I have is the H that's listed at the beginning of HX. So I know that it's a 1-to-1 ratio. Okay, awesome. 27.32 milliliters of NaOH at 0.0200 molar. Multiplied molarity times volume to get moles. Okay, 27.32 milliliters of NaOH. 0.0200 mole per liter. 1 liter is 1,000 milliliters. I know that I have 1 mole HX, 1 mole of NaOH. And even though I don't show it, we're going to just bring this down here because I don't have enough space. That leaves me in moles of HX. I need to divide by the volume of that, which is 64.38 milliliters. And of course, I have to convert that from milliliters to liters. Yippee skippy, that's exciting. So the thing that's really tricky about that one is knowing that it's a one-to-one relationship. And then everything should be straightforward. Times 0.02. I know it's 1-to-1, so yeah, we're going to divide by 1,000. It's a 1-to-1. I multiply by 60, or it's not multiply by. Divide that by 64.38, and I multiply by 1,000. And that gives me 0.008 molar HX. And now the question becomes, how many sig figs should I have? Well, this is 4. This is 4. This is 4. So I should be left with 4 sig figs. And again, I'm going to put this down here. 0.00847 molar HX for 4 sig figs. Okay? Questions, comments, problems about that? Awesomeness. Let's see what we have next after we clear this, because we know we're going to need to clear it. If the mass of the acid added to make the solution was 44.21 milligrams, what is the molar mass of the acid? What is the identity of that acid? Oh God. Oh Lord. All right, well, I just calculated something. Where'd my calculator go? You find my calculator. This is the molarity of the acid that I found. Okay. 0.00847 molar HX. That's exciting. If the mass of the acid added to make the solution was 44.21 milligrams. 44.21 milligrams. And I know that I had 64.38 milliliters. Oh, wait, no. Hold on. Do I need that? No, I don't. And let me erase this and let me tell you what I was thinking about. So I want to know how many moles that is. Well, okay. So if I want to know how many moles that is, I take this molarity, 8487 mole per liter. I know that I use 64.38 milliliters. And there's 1,000 milliliters per liter. Okay, if I do all of that math, now that gives me how many moles I had in this, right? 5.464 times 10 to the negative 4th moles. All right, I have moles and I have milligrams. 5.64 times 10 to the minus 4th mole divided by 44.27 milligrams. There's 1,000 grams in a milligram. Oops. Oh, sorry. There's 1,000 milligrams in a gram. That gives me moles per gram. Is that what I want? No, absolutely it is not. So how can I fix that? How can I change this to give me what I'm actually looking for? What I need is grams per mole. So I need to start with the 44.27 milligrams. Convert that to grams. 1,000 milligrams per gram. That gives me grams. I have 5.464 times 10 to the minus 4th moles. And that gives me, if I do that calculation, that should give me the mass that I'm looking for. Anyone 0.02 grams per mole. Okay, that's the molar mass of the acid. And what's the identity of the acid? Well, that's an interesting question now, isn't it? I think it is. So I know that this mass is 81.02 grams per mole. I know that there's one H on it, so I can subtract the 1.01 grams per mole from the H. And that's going to leave me with 80.01 grams per mole. And I can look at my periodic table and say, oh Lord, where do I see 80? Where do I see 80? Well, and I'm just taking a guess here that this is going to be a halogen. Why am I guessing that? I don't know, because I feel like it. Because I've got one H, one X. So it's likely that it's something like HCl, HBr, HI, something along those lines. So I'm going to check there first and see if I can find anything that's similar in mass as 80.01. And what I find is that bromine is 79.90 grams per mole. So my guess is that the identity of this particular thing is HBr, because this is very close to the 79.90 grams per mole that the Br is. Okay? Now, does that make sense for what I did and how I did it? Hopefully it does. So all I did was subtract the mass of the proton, see approximately what it was, and then look to find something on the periodic table that matched it. Okay? Again, I started with the halogens because those are the most likely things if we're talking about hydrogen and one thing attached to it for it to be. All right? Questions, comments, problems? I hope not. But if you do have questions, please let me know. All right, so that's our review from last time. I'm going to clear my calculator and I'm going to move that. I'm going to clear this because I don't need it right now and put that away. All right, let's go ahead and move on. Questions, and we asked for questions. Octet rule. Octet rule. An atom other than hydrogen tends to form bonds until it is surrounded by 8 valence electrons. Strangely, the outside valence orbitals in any atom are the s and the p. There are 8 electrons if those orbitals are full. 2 electrons in the s, 6 in the p. So that's where our octet comes from. Noble gases are really stable. They have a full valence shell of 8 electrons. So, awesome. So if everyone wants an octet, then everyone wants to be a noble gas. Hydrogen, however, needs 2 electrons to resemble the nearest noble gas, He. So that first row, we're looking for 2 electrons. Everywhere else, that valence is going to be 8 electrons. So that's what we talk about with the octet. All right, awesome. Chemical bonding. What is the most stable place on the periodic table? We just talked about this. Noble gases don't really react. And that's because the noble gases have a full valence shell. That valence shell is the outermost shell, the largest end of the atom. Full indicates 2 s electrons and 8 p electrons, total of 8 electrons, and that's where the octet rule comes in. Why do atoms lose or gain electrons? They want to be like the nearest noble gas. Okay, it's the most stable place for them to be. Now it's easier for a metal, the guys over here, and actually most of this table, it's everything, it's not from the stair step over is a metal. So it's easier for a metal to lose an electron to become like the noble gas before it. Because remember, all of these guys are going to lose the 2 in the S. Remember, these are Ds, so we're not going to lose those Ds. We're going to lose these S electrons to become like that noble gas, rather than gaining 6 or 7 electrons. That's complicated. So that's why things on the left side of the table lose electrons. Things on the right side gain electrons. These guys, it's easier to lose 2. These guys, it's easier to gain a few to come over here. Now, there are exceptions to that. Of course there are, but that's generally how we talk about that. Questions? Sweetness. Ionic bonds. Now, we've talked about this. Some atoms lose electrons to become cations, and some atoms gain electrons to become anions. What happens when the atom becomes an ion? Ions don't like to stay alone. So we've lost electrons or gained electrons. We now have a charge. Those charges don't like to be by themselves. So they try to find an opposite charge. A negative tries to find a positive to hang out with. The force holding a cation to an anion is called an ionic bond. It's ionic because they're both made from ions, and it's a bond. So consider sodium chloride. Sodium is a metal, and it's in group 1A. The electron configuration is 1s2, 2s2, 2p6, 3s1. It will lose 1 electron to ionize, making it like neon, which is the one before it. The electron configuration for Na plus is 1s2, 2s2, 2p6, which is the electron configuration of neon. Notice we lost that outer 3s electron. Chloride is 1s2, 2s2, 2p6, 3s2, 3p5. It gains an electron to become like argon. The electron configuration of Cl- is 1s2, 2s2, 2p6, 3s2, 3p6, which is the electron configuration of argon. So we've lost 1 electron for sodium, Na+. We've gained 1 electron for chloride, Cl-. Now that we have those two, they're attracted to each other and they form NaCl. That's an ionic bond. Anytime you have 2 ions next to each other, it's an ionic bond. Ionic bonds tend to be a metal to non-metal bond. Okay, so metal losing electrons, non-metal gaining electrons to do this. Now, I've drawn this strange structure up here, all right? I have Na, which has that 1 electron associated with it. I have Cl with 7 electrons associated with it. The Na gives up the 1 electron that it has to Cl, so that it's Na with no valence electrons, Cl with a full valence shell. Notice that 1 electron is from Na, the rest from Cl. Ionic bonds are a complete transfer of electrons to form noble gas-like structures. Okay? Awesome. That's an ionic bond. That implies that there's some other kind of bond. That other kind of bond that we talk about is covalent bonds. So what happens when I want to make a water molecule? Okay, water. H2O. Oh, okay, awesome. Now, are those electrons completely transferred? No. Why not? Because it takes a lot of energy to transfer electrons. The ionic bond that wouldn't be formed does not give a favorable state compared to non-ionized H and O. So it takes a lot of electrons to do, or energy to make that happen. But there are other ways that we can make that occur. So rather than completely transferring electrons, we can share. So oxygen still wants to be like any. It needs 2 additional electrons to make that work. But full transfer takes too much energy. So oxygen can share electrons with H. And if it does that, it can gain an octet of electrons without transfer of those electrons. Electron sharing is called covalent bonding. Sharing of 2 electrons, one from each of the hydrogens, makes a normal covalent, or from each atom makes a normal covalent bond. So each one will donate 1 electron to make that 2 electron bond. Okay? Now I like to think of the state of electrons like a divorce when there are kids. Either those kids are shared 50% to each parent, covalent bonding, not equal time with both parents, polar covalent bonding, or only with one parent, ionic bonding. So if it's only one parent, those kids have gone completely somewhere else. If it's a completely covalent bond, they're shared equally between those two atoms. But sometimes we have a situation where that electron spends more time with one of those atoms than the other. And that's what we call polar covalent bonding. All right. One further thing, when oxygen bonds with two waters, only 2 of the 6 electrons of oxygen are shared, meaning 2 electrons from 2H means that there are 8 around the oxygen. Sharing 2 electrons from 2 hydrogens gives it a stable octet. The electrons that are not being shared with H are paired and called lone pairs. Okay, sure. Give us a couple seconds, so I'll show you what that means. The determination of which situation it will be, the types of bonding that we just talked about, has a lot to do with electronegativity, Lewis dot structures, and the octet rule. So that's what we're going to talk about now. All of those things should not necessarily make sense at this point, but that's what we're going to be talking about in the next few slides. Okay? Octet. Oh, wait. Questions. Sorry. A little caught up in what I was talking about. Lewis dot diagrams. Okay, let's talk about those. So Lewis dot structures explicitly show the electrons in the valence shell of an atom. So for oxygen, there's 6 valence electrons, 2 in the 2s shell and 4 in the 2p. So 1, 2, 3, 4, 5, 6. 2, 4, 6. If that is the Lewis dot structure for O, here's the one for H. H has 1 electron, so it's right there. Awesome. Notice that I've drawn these differently. These are dots, these are X's. And I do that so that I can show you that when it's bound, these two make water, like this. So your hydrogen with its 1 electron, your hydrogen with its 1 electron, your oxygen with its 6. 2, 4, 5, and 6. These 2 electrons, one from hydrogen, one from oxygen, form a bond between hydrogen and oxygen on both sides, okay? All right, that's awesome. Now what? Let's look at oxygen. Since it's sharing 2 electrons with H, and those 2 electrons from the 2 H's, and the 2 lone pairs, there are 8 electrons around the oxygen. 2, 4, 6, 8. The sharing gives oxygen access to 8 electrons, and H access to 2 electrons. What's the difference? Why? Hydrogen only has space for 2 electrons, since the valence electrons appear in the 1s shell, so only 2. Therefore, in order to be like the nearest noble gas, He needs 2 electrons. Oxygen, in order to be like the nearest noble gas, Ne, needs 8 electrons for the 2s and 2p orbitals. S holds 2, p holds 6. Awesome. That's cool. So now I understand, sort of. Molecular Lewis structure example. So draw the atomic Lewis dot structures for carbon and oxygen. So carbon has 4 valence electrons, 2s. It's 2s2, 2p2. So 1, 2, 3, 4. I put 1 on each side because you'll figure it out eventually, but there's 1 on each side. The Lewis dot structure for oxygen, which we've already drawn, 1, 2, 3, 4, 5, 6. You're the 2s2, 2p4. We know that we can make CO2. We know that. We've seen that formula. We've seen that written all the time. Like we combine C, O, and O to fulfill the octet rule. We can combine 1 oxygen electron with 1 carbon electron to make a bond. And the same on the other side. Then we still have only 7 electrons on each oxygen and 6 for carbon. So 1, 2, 3, 4, 5, 6 from oxygen, 1 from the carbon, 1 from the carbon, 1, 2, 3, 4, 5, 6, 7. 7 on each oxygen. Not completely happy. And of course, this doesn't give us any of the other electrons for the carbon. So that's not really what we're talking about, is it? Probably not. So let's see what we can do with that. What if we make 2 bonds? What if we share 4 electrons between carbon and oxygen? So I had 4 carbon electrons, 1, 2, 3, 4. And I have 1, 2, 3, 4, 5, 6 on oxygen. So oxygen still has 6. Oxygen still has 6. Carbon has 2, 4. But now we have, instead of just 2 electrons between carbon and oxygen, we have 4. 4 electrons is a multiple bond. This specifically is a double bond. That's awesome. Note that carbon is sharing all 4 electrons that it has. Oxygen is using 2 of its electrons to form a double bond with carbon on each side. It's a double bond since both molecules have 4 electrons on 2. Now, so we've got 2 bonding electrons for oxygen, and then 1, 2, 3, 4 non-bonding electrons on oxygen. Okay, awesome. Well, N2, what does that look like? How many bonds? Well, each nitrogen has 5 valence electrons. 5. Oh, Lord. We can draw 2 on one side, 1, 2, and then 1, 2, 3 on the other side. 1, 2, 3 on this side, 2 on this side. So I have all 5 of mine for each one of the nitrogens. 2, 4, 6, 7, 8. I have 8 electrons available for each nitrogen. But since I have 2, 4, 6 electrons between the 2 nitrogens, that's a triple bond. Now, each line represents 2 electrons, which we call a bond. So that's a triple bond. Okay, awesome. Questions about that? I hope not, but if you do, let me know. So let's talk about water again. So let's draw a Lewis dot structure for water. Oxygen has 6 valence electrons. Each hydrogen has 1 valence electron. If we have 1 bond between the H and the O, then oxygen gets an octet and H gets a duet. Can't go any further. There's no other place to put electrons. He's happy being like He. So that gives us this thing right here. Well, okay, fine. But that leaves 4 electrons on oxygen that are not shared by hydrogen. What does that mean? Well, strangely enough, what we see is that all of those unshared electrons means that this end of the molecule is a net negative, and this end of the molecule is a net positive. We can show this by showing this arrangement here, which shows high electron density around one end of it and low electron density around the other end of it. Okay, yippee skippy. Why is that important? Well, it must be because I told you about it, right? So why is it? So what? Electron density on one side of the molecule is much higher than the other. We call that a polar bond. Now remember, I mentioned polar bonds before. We said that there was unequal sharing of electrons between the 2 atoms that were there. Okay. The electrons are not evenly shared. This leads to ease in dissolving salts. The negative end of water can stabilize the cations. The positive end of water can stabilize the anions. Water likes to interact with a polar or charged particle because of this. Now, how do I know if things are not equally shared? That has to do with electronegativity. Remember when we talked about periodic trends before? And I said that Cl really wants electrons, but that Cs doesn't? The same is true for electronegativity. It's the same trend. So as I go across the table from the alkali metals to the noble gas, well, not to the noble gases, but to the halogens, there's an increase in electronegativity. And as I go from the bottom of the table to the top, up towards fluorine, then I have an increase in electronegativity. Electronegativity is defined as the ability of an atom to attract the electrons in a chemical bond. Okay, so same trend, awesomeness, and that's how much it wants to hold on to those things. All right, and now for the good news. Yes, because there is good news. We will not do electronegativity calculations, but you do need to know the trends. We'll also not do calculations on dipole moments, which is in the next slide. Okay? What is a dipole moment? Oh dear Lord. So let's talk about the difference between CO2 and H2O. So we drew this before. We had the double bonds between oxygen and carbon. We have two sets of non-bonding electrons on each oxygen, this structure right here. We have hydrogen here, two electrons shared, two non-bonding pairs of oxygens on the water. All right, so the electron density on water is on one end of that molecule, but it's pulling to the ends of CO2. So we talked about this structure. Notice that these lone pairs on the oxygen pull the electrons further this direction. So there's a partial negative and a partial positive down here, partial negative here, partial positive here. But on this one, we have the same pull from carbon to oxygen on this side as we do on this side. So there's no net pull in one direction. Since we don't have a net pull in one direction, then that particular molecule doesn't have a net direction for electronegativity. The water does, and we call that a dipole moment. It means that the molecule has a net end that is negative and a net end that is positive. Not just the bonds, but the whole molecule. Okay, so even though we know that each of these bonds, the electrons are drawn more to the oxygen than to the hydrogen, that is true. But we also have a net pull of electrons towards this end of the molecule as well. All right, so that's a dipole moment. Questions about that? Sweetness. Drawing Lewis structures. So we talked about drawing Lewis structures for some atoms. We've shown you a couple for some compounds. Let's talk about how we drew those structures other than doing what I said to do. So how does that work? As a note, this set of rules will not be on the test. You will have to know it. I'll present the rules on the next slide, and then we'll view them as we do the examples listed below. Just as with solubility rules, the rules are applied in the order of appearance. So we're going to consider the following molecules: PCl3, NH3, and BrO3-. Okay? Let's go and take a look. PCl3. Let's talk about our rules. We sum the valence electrons from all atoms and take charge into account. So if there's a negative charge on that, we have to add an additional electron. If it's positively charged, we lose an electron from that count. We write the symbols for each atom. Connect atoms with a bond signaled by a line. Each line is 2 electrons. We complete the octets around the atoms bonded to the central atom, so the ones on the outside. We place any leftover electrons on the central atom. If there are not enough electrons to give the central atom an octet, we try multiple bonds. And then we check the formal charge of each atom and minimize it if you can. The best structures have no formal charge, but if negatives exist, they have to be on the most electronegative atom. Bunch of gobbledygook. So what the hell am I talking about? Well, let's see. I mentioned formal charge. So formal charge and alternative Lewis structures. Formal charge is the electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. So formal charge equals valence electrons minus half of the bonding electrons minus the non-bonding electrons. This is only done after all unshared non-bonding electrons are assigned to the atom that they are on. For any bond, half of the electrons are put on each atom in the bond. And this is done for all atoms in the structure. Formal charge is not related in any way, shape, or form to ionic charge. This is not a transfer of electrons. It is simply bookkeeping for us to be able to see if an atom is happy. Okay, that's all it is. All right, sweetness. So, how do we go about talking about this? So we're going to consider CN. Cn minus. Before we get to some of those other examples that we talked about. Cn minus. Let's assign formal charges here to see if we can do it. So formal charge equals valence electrons minus half the bond. Sorry, give me a second. I apologize. Didn't mean to do that. There we go. So formal charge is the valence electrons minus half the bonding electrons minus the non-bonding electrons. All right. So let's see if we can do this. So carbon contains 4 electrons in its valence. 2s orbital electrons and 2p electrons. Nitrogen has 5. The charge on this is -1. So 4 plus 5 plus 1 is 10 electrons total. So I'm not going to show you yet how I drew this, but this is the structure that I came up with. Carbon has 2 electrons on the outside, 1, 2, 3 in the center, 3 and 2 there. Now, carbon normally has 4. 1, 2, 3, 4, but the -1 is put here on the carbon. So this is a structure I have. Notice that it's bracketed and there's a negative here to indicate that we have an extra electron. Formal charge. Carbon normally has 4 valence electrons. We subtract half of the bonding electrons, so these 2, 4, 6 electrons here, minus the 2 from the non-bonding electrons. That gives me a formal charge of -1. Nitrogen normally has 5 electrons. I subtract half of the bonding electrons, and then the -2 for the non-bonding electrons. That gives me a formal charge of 0. Okay? So that's how we get that. Now, we'll get back to how we got to that structure in a few minutes, but that's how we assign it for that particular structure. All right? PCl5. All right, PCl5. So phosphorus has 5 electrons. Chlorine has 7 electrons. There are 3 of them, so total of 21 electrons for chlorine. It gives me a total of 26 electrons. Now, in order to do this, per the rules that I was given, let me pull this guy up so that we can talk about how we do this on our own. So let's draw a phosphorus. Let us draw a phosphorus. I'm going to have 1 chlorine over here, 1 chlorine over here, and 1 chlorine over here. Now remember, we had phosphorus having 5 electrons, chlorine, each one having 7 times 3, 21. Total for all of those is 26. Now, I have 3 chlorines around the phosphorus. I draw 1 bond, 1 bond, 1 bond. So 2, 4, 6 electrons are taken up there. So I subtract those 6. I'll leave you with 20 electrons. 20 electrons. Now, I have 2 electrons here. I need 2, 4, 6 to make chlorine happy. 2, 4, 6 to make that chlorine happy. And I need these to make that chlorine happy. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons taken up, filling the octets for the outer atoms. That leaves me with 2 electrons left. So I'm going to put those on this phosphorus right here. Okay, so I have 2, 4, 6, 8 electrons associated with each chlorine. 2, 4, 6, 8 associated with the phosphorus. So that's the structure as I came up with it. And that's the one that we saw when we were looking at this slide. Awesomeness. Okay. So the 3 bonds equal 6 electrons. 3 non-bonding pairs on chlorine times 3 is 18 electrons. It's a total of 24. That leaves me 2 electrons to put on the phosphorus. Oops, sorry. Formal charge for the phosphorus. Normally, phosphorus has 5 electrons. It's right under nitrogen. So 5 minus half of the bonding electrons, so 2, 4, 6. Half of those 6 minus the 2 that are non-bonding up here gives me a formal charge of 0. Formal charge in each chlorine has 7 electrons normally. We subtract half of the 2 electrons that are in this bond minus the 2, 4, 6 non-bonding electrons. That gives me a formal charge for each chlorine as 0. Okay? So we've now drawn our structure. We used all of our rules to draw our structure. We assigned formal charges. Everybody was happy. Awesome. Let's try another one. NH3. Okay, NH3. Well, let's see how we get NH3. Well, I want to do NH3, and I'm going to do that in blue just so I can keep track of things. Nitrogen has 5 electrons. Each one has 1 electron. There are 3 of them. It gives me a total of 8 electrons. Okay, nitrogen, hydrogen, hydrogen, hydrogen. Whatever we put first is typically the one that's in the center, but we also know that this has to be the case in this particular instance because hydrogen cannot bond with more than one thing. So I have 1 pair between each. That gives me 2, 4, 6 electrons that are already taken up. So we have 2 electrons. Those 2 that are left go on the nitrogen, and that leaves me with the structure that I have here, NH3. So again, 3 bonds times 2 electrons, 6. That leaves 2 electrons to go on the nitrogen. Formal charge for the nitrogen. I normally have 5. I subtract half of the 2, 4, 6 bonding electrons minus the 2 non-bonding electrons. It gives me a formal charge of 0. Formal charge for each H. Hydrogen normally has 1 electron plus half of the 2 electrons in the bond. That gives me a formal charge of 0. Awesome. We can do this. It's not as bad as we might think. BrO3. Right. Well, let's just do some basic trial and error on BrO3. So, oops. BrO3 minus. So, bromine, 7 electrons. Oxygen, 6 electrons. There's 3 of them. Gives me a total of 18. And then I have a negative charge. So that's 1 electron. 7, 8, and 18 is 26. 26 electrons. Woohoo! So I'm going to put my Br in the middle. I'm going to have oxygen. 1, 2, 3. 3 bonds. So 26 minus 2, 4, 6. These are 20 oxygens, or 20 electrons. I'm going to do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Because I'm supposed to fill the octets, the ones on the outside, first. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2 electrons that I put on my bromine. Okay, so that's how I got there. Now, I know that when I do this, I'm going to need to have a bracket. It goes around this to indicate that there's a negative charge on the entire complex. That's how I get here. Now, let's take a look at this structure. Formal charge for bromine. Bromine normally has 7 electrons. I have 2, 4, 6 electrons in the bond, so I subtract half of those 6 electrons, minus the 2 electrons from the non-bonding pair. That gives me a plus 2 charge. So half of 6 is 3, minus 2 is 5. That gives me a plus 2 total charge. Formal charge on each oxygen. 6 minus half of the 2 electrons in the bond minus 6 is a negative 1. So each one of these has a negative 1 charge. Negative 1 here, negative 1 here, negative 1 here. Total of negative 3 plus 2 gives me a total of negative on the the whole thing. Now, technically this works. This overall charge is what it's supposed to be. However, the charge on Br is positive. That's not ideal. So let's see what else we can do. What else can we do? Well, there are a couple of things that we can do. We can take and move electrons. So we try moving one pair of non-bonding electrons to a double bond. So we take one of the pairs over here on this oxygen on the left. And instead of having it being a non-bonding pair, we move it in and make it a bonding pair. So that changes our formal charge, right? So let's look at our bromine first. Br normally has 7 electrons. We subtract half of the bonding electrons, so 2, 4, 6, 8. So half of those. Minus the 2 non-bonding, that gives me Br plus 1. Formal charge on the oxygen with the double bond. We normally have 6. We subtract half of the 2, 4 that are here, minus the 2, 4 non-bonding. That gives me a formal charge of 0. So this one is 0. Formal charge in the oxygens without the double bond. I have 6 minus half of the 2 minus the 2, 4, 6, which gives me a negative 1. So again, overall charge is negative 1. But we still have a charge on the bromine, and we still have, and that's not ideal. So this one is happy. We have a lot of charge everywhere else. Not great. What else could we try? Well, turns out we can try the same thing again. We try moving another pair of non-bonding electrons to a double bond. So now we're doing it on the one on the right. So we've taken one of these non-bonding pairs and moved it in and made it a bonding pair. So now my bromine, let's talk about bromine, normally has 7 electrons. We subtract half of the 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, minus the 2 non-bonding. That gives me a formal charge of 0 on bromine. Formal charge of the oxygen with the double bonds. We have 6 minus half of the 4, 2, 4, minus the 4 non-bonding. Each one of those is 0. So 0 here, 0 here, 0 here. Formal charge of the oxygen without the double bond. We normally have 6 minus half of the 2 minus 2, 4, 6. That gives me a negative 1 on the oxygen. And that matches the negative 1 on the entire thing. The negative 1 on one of the oxygens is a good place for that to be, because that oxygen is actually more electronegative than the bromine because it's higher in the table than the bromine is. So this is the structure that we like. Now, are we happy with that? Well, let's see. So what do we really do in the last exercise? We move non-bonding electrons until we minimize the charge. Ideally, we want the charge to be 0 on all atoms in the structure. Can't always do that. If we need to have charges, then those charges need to be on molecules that are able to handle them. Negative charges go to the most electronegative atoms present. Remember, up and to the right are more electronegative, so oxygen's more electronegative than bromine. Positive charges need to be on a less electronegative atom. Keep moving until we have as few charges as possible. Okay. So let's try this. It worked so well the last few times. Let's try it one more time. Let's move one more non-bonding pair from this bottom oxygen in to make another double bond. So now we have bromine, which normally has 7, minus half of the 2, 4, 6, 8, 10, 12 from the bonding pairs, minus the 2 from the non-bonding pairs. And what does that give me? 7 minus half of this would be 7 minus 6 minus 2 is negative 1. Oh, Lord. Formal charge of the oxygens with the double bonds is 0. So my bromine is a negative 1 charge. All the oxygens is 0. Charge overall still works. It's a negative 1 charge. But it sits on the bromine, which is not the most electronegative species in the molecule. So this structure is not favored over the one that has only 2 double bonds and 1 single bond. So the structure from the slide 29 is the one that's preferred. 29 being not that one, that one. This structure is preferred. Okay, great. What the hell does that mean? Well, I now have a preferred structure. But what does that mean? What on earth are we talking about for that? We actually have two distinct kinds of oxygens, and does it matter how I draw it? Does that mean that we have two distinct oxygens that we can look at? And the answer is no. Actually, no. If we look at this molecule in any way where we can see electron density, we're not going to see that there's two that are different than the other one. It's not how it works. Okay? What we do see is that we have the same electron density over all of the oxygens in that species. And that's because the interconversion of the double bond to the single bond is enormously fast. Okay? So we can go from where our double bonds are both at the bottom to where the double bonds are at the top and the right, and our double bonds are at the top and the left, and they all interconvert between each other. All right? So what do we call those structures? They're called resonance structures because they all interconvert, and so they say they resonate. Okay, so we can distinguish each O. So we designate them in a way we can distinguish. We put numbers on them and say, look, here's how we can do this. The average of those structures is what we see if we look at the compound. Instead of two with two bonds and one with one bond, each will have an electron density equal to 1.5 bonds. Okay, that's what it looks like in reality. All right, but we have to be able to draw these resonance structures so that we have some idea what we're talking about when we draw these things. All right, so those are resonance structures. Yahoo! So let's draw one more. Let's talk about the Lewis dot structure for O3. All right, so O3 minus. 2 seconds. Now, I'm going to skip down so that we can actually see what this looks like. So oxygen has 6 electrons. Actually, I'm going to go back. Let's draw the Lewis dot structure for O3. And I'm going to do this on the whiteboard so that you can see the logic that I'm using to do this. And then you can take a look at the slides that I put together so you can see that in without having to draw it all. Okay? And so we want to talk about O3. Okay. 1, 2, 3 oxygens. Now, each oxygen contains 6 electrons. There are 3 of them, so we should have a total of 18 electrons. I know we need to draw one bond in between these two. All right, so 4 electrons taken up by that. That leaves me with 14 electrons. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. Okay, 12 electrons. Leaves me with 2 to put on my central. Full octet on this on the right, full octet on this one on the left, but I don't have a full octet for the oxygen in the center. Okay. So how do we fix this? What do we do about it? Well, we can move non-bonding electrons, right? We talked about that before. So let's try it for this one. We'll take those 2 non-bonding electrons and move them in here to make that double bond. Okay, cool. Now, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody has an octet now. That's cool, right? So we got to this point and we said, nope, not entirely happy. So we got to this point, all right? So the second drawing is shown here. Formal charge on the outer oxygen with the double bond, 6 minus half of the 4 minus 4. The formal charge on this oxygen with the double bond is 0. Formal charge on the outer oxygen with without the double bond, 6 minus half of the 2 minus 2, 4, 6 gives me a -1. Formal charge in the inner oxygen, 6 minus half of the 2, 4, 6 minus 2 is +1. So the overall charge is 0. We still have a lot of charge. And each oxygen has an octet, but it's not a great structure. I mean, is it always going to be like this? No, not always. Sometimes it can look like this. So instead of, oops. So this is the structure that we initially had. And then we took 2 of these non-bonding electrons and pulled them in to draw a structure that looks like this one. Okay, now that's perfectly happy, right? Now, formal charge on this outer one, we have this as 0. Formal charge on this one is -1. Formal charge on the inside is +1. So our overall charge is 0, just like it should be. But it doesn't always look like this, does it? No. Sometimes double bond is on this side. And actually, there should be another lone pair out here, and I apologize for that, but there should be another lone pair right there. So let's put those in before the world goes crazy. And now we're happy. Okay, awesome. So that's what we like there, all right? So that's what we see there. Again, they're two different structures that realistically talk about the same species, but they interconvert. So we have to be able to draw that on a test. How do we do that? We have a fast interconversion. So we have a double bond here, positive and negative there. Interconvert to the other side. So this one now becomes the negative oxygen. This is still positive, and this is the double bond. So that interconversion is fast. All right. We can draw this as a resonance structure just like we did before with the brackets around the whole thing. Or we could draw it like this with a delocalized bond. Okay. Either one of those is an appropriate way to do it. All right. So that is, again, a resonance structure. Questions, comments, problems on that? Okay. Awesome. Trying to get rid of these. I apologize. Questions about that? Sweet. Let's keep going. Now, exceptions to the octet rule. Is it possible to always have an octet? No. Hydrogen and helium cannot have an octet. The best they can talk about is a duet. So 2 electrons for those 2 species. Sometimes we can't do it because we have an odd number of electrons, such as nitrogen. So NO, nitrogen has 5 valence electrons, oxygen has 6. It gives us a total of 11 available. 1 bond between the nitrogen and the oxygen gives me 2 that I can take out of that. That leaves me with 9 electrons to place on the atoms to try and fill our octets. I start with the oxygen, it's the most electronegative. Let me show you what I'm talking about over here. So if we want to talk again about NO, nitrogen, 5 electrons, oxygen, 6 electrons. We get a total of 11 electrons. NO, 1 in between them gives me 2 electrons. So that leaves me with 9 electrons that I need to distribute. 2, 4, 6 there. Leaves me with 3. 1, 2, 3. Okay. So I've got all my electrons distributed there. Now, I don't have an octet for nitrogen. I do have one for oxygen, but this is not the greatest structure in the universe. So one way that I can fix this is by moving one of these non-bonding pairs like this. Again, that means we still have the same number of electrons, but now we have 2, 4, 2, 4, 6, 8 are on the oxygen still. 2, 4, 6, 7 are on the nitrogen. Not perfect. Absolutely not perfect. But we can't do any more than that. There's no way for us to get any closer. This is the closest we can get to having a full octet on both. Now, if we talk about formal charge for the nitrogen and for the oxygen, 5 electrons here, we subtract half of the bonds. So there's 4 electrons in that, minus the 3 that's there. That gives me formal charge of 0. So 5 minus 2 minus 3. So that gives me a net charge of 0. Oxygen should have 6. I subtract the half of the bonds minus 4 gives me a total that gives me a 0 charge on that as well. So my formal charges are happy. I just can't get an octet on that nitrogen, and that's because I have an odd number of electrons. Okay, so that's what we're talking about for that. Questions, comments, problems on that? So those are basic exceptions to the octet rule. Another thing we have is this species BF3. Now I'm going to show you, you obviously have this to look at. Let's talk about how we get to that structure. BF3. BF3. So let's talk about boron. Let's talk about fluorine. Now fluorine's the easy one. It has 7 valence electrons. There's 3 of them, total of 21 from there. Boron has 3 valence electrons because it's in group 3A or 13. So it has 3 valence electrons. It gives me a total of 24 that I can deal with. I have B, F, 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 2, 4, 6 in the bonds. Gives me 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I can fulfill the octets for each of the fluorines. I have 6 electrons around the boron. But I have no more electrons I can put anywhere. So that's the best structure I can come up with. Yippee skippy. Is that a full octet? No, absolutely it is not. There is something I can do. And I'm going to show you that by moving this guy up here. Clean that up a little bit. Okay, unhappy BF3. It's there, but it's unhappy. So let's see if we can find some way to make it happy. The way that I can make it happy is to find a molecule that has a lone pair that is not being shared. Here's one I know of, NH3. Now, I know that NH3 is something like this. Nitrogen has 5 electrons, each H has 1, 3 of them gives me a total of 8 electrons. We've drawn this before. 2, 4, 6 taken up with the bonds. That leaves me with 2 left that are not bound and a lone pair, as a lone pair. All right, awesome. I drew that. But here's something that you may not have thought of. if I take and I put this like this, what does that show me? Well, that shows me that I can give boron an octet by sharing the lone pair on nitrogen. Okay. It is possible for it to do that. Okay. So that is something that we can do, and it makes this complex. It is one of those exceptions to the octet rule that comes from trying to get an octet on boron. All right? Questions, comments, problems on that? Sweet. Let's go back to our slides. One other exception that we want to talk about, PF5. So PF5, our molecules that have more than an octet around the central atom, just based on the formula, I know I'm going to have to break the octet rule. In order for phosphorus and fluorine to have, for there to be 5 of them, I'm going to have 10 electrons, 2, 4, 6, 8, 10. Now, is this a happy structure? Actually, yeah, it is. There are 5 electrons that are associated with phosphorus, just as there should be. It being under nitrogen, it should have 5. But there are 1, 2, 3, 4, 5, 6, 7 associated with each fluorine. So this is a structure that has no formal charge. Okay, this is a happy and stable structure, but it requires an exception to the octet rule. Since phosphorus is in row 3, there are unused 3d orbitals present that can be used to make such bonds. This is known from row 3 down. So we see this in anything that's in row 3 down. All right. So this is another exception to the octet rule. So bigger than the octet. Okay. We talked about BrO3 minus. This is one that we talked about before. This, again, is one of those situations where we have more than an octet. So 2, 4, 6, 8, 10, 12. And again, that is because we have 4D giving us the availability to do that. All right. So that's that there. And we didn't really talk about it before, but that is another exception to the octet. Questions, comments, problems on that? Well, that brings us to the end of chapter 7, or lecture 7. Now, remember, lecture 7 is almost all about drawing Lewis structures, assigning formal charges, making sure that it's a happy structure, trying to see if we fulfill the octet rule. That's all of what that is. Now, that's all drawing stuff. We'll talk about how that impacts some other things in the next lecture, in lecture 8. But that's what we have for lecture 7. If there are any questions, comments, problems, please let me know. I will be happy to answer any questions that you have. But that takes us to the end of lecture 7, and I will see you guys later. All right, thanks. Talk to you later.